right, so let's see our contingency tables in action and when they're useful and what they can do for us. So we have an exercise here, and the first thing I want you to do is to translate all the given probabilities into probability notation. So just glancing through here, we can see we have 3 different probabilities that are given and 1 that we're looking for. So I'm going to go ahead and set you up with these little empty probability notation pieces. And I would like you to pause the video, go through, and try to figure out what exactly you've been given, and what you're looking for. Remember, the first thing you want to do is read through and sort of get an idea of what's going on, and this question makes it super easy. It defines what our 2 different outcomes or events are. So we're looking for computer science majors and discrete mathematics, and the 13%, the only thing here is about being a computer science major, and then it starts in with a new sentence. So this is just event A. 15% have discrete mathematics, and 84, and we start a new probability, so this is just event B. And 84, let's see, are not computer science, so that's an A with a complement, and have not taken discrete mathematics, so that's a B with a complement. And I'm going to use the union or the intersection notation just because I didn't give myself enough room to write and. And then lastly, we're looking for the probability of a computer science major, which is A, and not taking discrete math, which is B complement. And then we don't have an and or an or between them, but we do have but, which is another conjunction word, which means and. So our final probability that we're looking for is A and B complement. So if you went and looked at all of your different probability formulas and things that might help you out here, you're not going to find much help. The closest thing is that we have our A and B formula, but this requires us to have a given, and we do not. So we're kind of SOL when it comes to the formulas, and that's when a contingency table would help. So a contingency table is going to help It's going to come to the rescue if we have an and. The ands are what the contingency table displays, so they're going to be really useful. And you can see right here we do have an and. So let's put all these things in the table. So first we have probability of A. Now remember from our last video, A by itself does not go here because this is A and B. We're going to go all the way to the total part of A, and we're going to put our 13 there. And I'm going to even go ahead and just make sure that I label these because I don't like that we use letters that aren't very useful. So we got computer science and discrete math. B by itself, again, don't stop early, go all the way to the total section, is 15%. And A complement, B complement is where these 2 pieces intersect, is 84. And we want to find A and B complement. That's what we're looking for. All we need is one more piece, and that was what I was telling you guys about the fact that we always have a total of 1. Because of this, we can use the fact that all of our columns and rows sum. If 13% of people have taken computer science, that means 87% have not. And if 15% of students have taken discrete math, that means 85% have not. And we can do the same thing with the internal columns and rows. We need to figure out what adds to 84 to give us 85, just 1%, and what adds here and here. And it's nice because it kind of built in checks itself with that final value that you put in. So the question we originally had is very easy now. We can just pull that straight off the table. It's 0.01. So I want you guys to take a moment and go through each of the different probabilities that are asked for next, translate them into their notation, and then figure out what they would be based on the table. We are very good with the table though, so we should be pretty good at this question. So pause the video, try it out, and come back. Alright, so if you come back, we have taken discrete math, but, which is our keyword for and not a CS major, so discrete math was B, not CS is A complement, Again, no need to use a formula here. This is straight off the table, right? B and A complement intersect here. Next one, probability someone who has taken discrete mathematics is a computer science major. There is no and, no but. So this one we have to think a little bit harder. The fact is, in the first one it said probability A student. Here it says what's the probability that somebody who has taken discrete mathematics. This is what we know. This is very subtle. Usually on tests I'll use given, of, or if, something to help you out here. But in this case, we know they've taken discrete math, and we want to know the probability of them being a computer science major. Now this is when we need to go to our formulas for. Or we just do this common sense wise. If we know they've taken discrete math, we know we're in this row. And then we're interested in the fact that they are a computer science major, so this is our part of our whole. But if you use the notation or the formula, this is exactly what the formula is set up as. So we're just pulling off 0.12 divided by 0.15, which gives us 0.8. All right, and then the last one before we get to the final question. Probability has someone has taken discrete math, which is our B, or is a computer science major, which is our A. B or A. Again, this is a formula one. So when you have these tables, which is going to happen on the worksheet this week, it is just make sure that you realize if you're looking for one of the things by itself, you can get that from the table. If you're looking for an and, you can get that from the table. If you're looking for or a given, this is when you have to use the formulas. So in this case, the formula for or, remember, add them together, subtract off the intersection we counted twice. So in this case, we're looking at 15% of people having discrete math, 13% being computer science, and then subtracting off the 12% that had both. All right, so the last one. In the video, I very briefly said here's some ways to test independence, and now we're actually going to get to see it in action. So the last piece here says, are they independent events? Justify your response. So I gave you two methods to check this. Method one, as soon as we see the word independent, remember we have this sweet rule, and this should be on your note card. The big old independent, and then this is what we're going to write down. So we can use this to check to see if something's independent, as well as a rule to help us out if something's independent. So in this case, A and B, well, this we can pull right off of the table as 0.12. Probability of A was given to us. This was 0.13. And the probability of B was given to us as 0.15. Excuse me. All right, so we multiply those two probabilities together. We get 0.0195. Does that equal 0.2? No. So the answer is no, they are not independent. And we can say because probability of A and B does not equal probability of A times the probability of B. All right, so that's method one. Method two, I like because it gives us a little more information, but it's a little bit trickier for students, I find. Method two is the fact that we know our conditional, having that additional information doesn't give us any more information. So we already found a conditional. If knowing B gives us no more information about A, if they're independent, then this should just equal the probability of A. Which we know both of these things, right? We figured this out as 80%. Probability of A was given to us as 13. These are not the same, so again, we could say they're not independent. But here I even like this because we have a little bit more information. They're not independent. We can even say the B made it much more likely to have A, right? This was like a woman being much more likely to own a pink shirt than a man. So we could give ourselves even a more lovely explanation here, because the students who have taken discrete math are much more likely, because that's our B, right, to be CS majors. And that is 80% versus that 13%. All right, so that's how we can use either one of those formulas to test independence and what that actual response should look like if this were a test question.